Today we're going to talk about causality. The problem of causality is not that the statistical method, in this case ordinary least squares, is getting things wrong. The problem is that we interpret incorrectly what OLS is showing us. So the mistake is in the interpretation, it's not in the mathematics or the statistics. So from a mechanical point of view, nothing is going wrong. It's just that we, when we look at the results, interpret things incorrectly. There are three well-known cases where you can make such interpretation mistakes. So there's the fork, the pipe and the collider, and we go over these in this lecture today. And we go over each of these with using the same procedure. So first we're going to generate the data, so that there's actually no discussion about the interpretation. We hard code with Python the relevant causal effects, so we know exactly what should come out of the regressions that we run. Then we are going to use OLS on the data that we generated ourselves, and first we're going to give an incorrect interpretation of the result. So we give an interpretation of the result which is actually at odds with the way we programmed our own data. And then we're going to dig a bit deeper. So a fork is a situation where there's a variable x which is caused by a variable z, and z is also causing y. So what we're going to do is to run a regression from y on x, and that will give the idea that x is causing y. Yes, so the regression suggests that if a policymaker would increase x in one way or another, he would increase y. And that's actually incorrect, because the way we're going to generate the data is that there is no relationship between x and y. There's going to be a relationship between z and x and z and y, and that suggests the relationship between x and y. So let's generate our data. So again, we're going to specify a sample size, and this time we're going to work with a sample size of 100. I'm going to use a slope of x equal to 1. And there's going to be a slope of y equal to -1. So feel free to program different slopes. There's going to be a constant x which is equal to 2, and there's going to be a constant y which I'm going to choose equal to 0. So first we generate the variable z, which is going to be equal to TensorFlow random. I'm going to use the normal distribution. And it's going to be of size sample size. Then we're going to have the variable x, which is going to be equal to the slope of x times z plus the constant x, and we're going to have a noise term tf random normal with this sample size, and for y we want to have very similar expressions, so we're going to be slope y times z plus constant y, and this is actually going to be exactly the same, so I'm going to copy it. So as you can see, there is no relationship between x and y. When you look at the equation for y, there is no x in here. And if you look at the equation for x, there is no y there either. The only thing that happens is that I have this random variable z, which affects both x and y. Now it's going to be easy if we're going to put these variables into a data frame. So we're going to use pandas and then the data frame command for that. Pandas data frame. So to create a data frame in pandas, you create a dictionary. So we're going to have a column X, which contains the vector X. It's going to be a column Y, which contains the vector Y. And there's going to be a column Z, which contains the vector Z. And just to be sure that everything happens the way I thought it would happen, let's look at the head of that data frame. So that looks fine. So I have a data frame with 3 columns, X, Y, and Z. So now I want to run a regression. And in order to run the regression again, we're going to use stats models. As I said above, you don't need to know the syntax of stats models, but I need a simple package that's going to be generating OLS output in the way you know it, like from Stata or other programs that you might be using. So I call this the results for the fork incorrect, because we're going to incorrectly interpret what's going on. So if you want to understand the syntax that I'm using here, simply go to the website of stats models. So I'm going to specify a relationship between Y and X. The constant is assumed. So it's going to be automatically added, and I tell which data set we're using here. So that's the data frame fork. And then I want to fit. Now we're going to get, results incorrect, the summary. So here we see the results. And the thing that we're interested in is the X variable. So the OLS here suggests that there is this effect of -1 of X on Y, and this result is highly significant. Yeah, so there's a huge t value associated with it. So you might have this idea that these results suggest that X is actually causing Y. Yeah, so that's always dangerous, because OLS regressions do not show causality, they simply show correlations. And it's indeed the case that X and Y are correlated, because they're both caused by Z, but it's not the case that X is causing Y. So how can you solve the problem of a fork? I'm going to do something which is very similar, so I'm simply copy this code block. I'm going to paste it, so now I'm going to look at this, the correct version, and that basically says that I'm going to control for Z. So I'm going to look at the effect of X on Y, controlling for Z. So the data is still the same. So I'm still using the fit method on this. And then I'm going to look at the summary. So now if you look at the results, what we're going to see is that there is a significant effect of Z on Y. It's highly significant, a t-value of 11. So that's correct, because that's actually the way we generated the data. And once we started controlling for Z, you can see there is no significant effect left of X on Y. So in case of a fork, the way you solve the fork is by adding other variables that might actually also have an effect on Y. And in this case, it has the only effect on Y. There is no effect of X on Y. There's only an effect of Z on Y, and once we control for Z, we can indeed see in the OLS regression that there is no effect of X on Y anymore.